Hey everyone, Patrick Kennedy here with Microchip. In this video we are going to take a look at the new direct memory access or DMA features available on newer 8-bit PIC microcontrollers. I'll cover the basics of what direct memory access or DMA is, how the DMA peripheral works, and lastly the significance it will play in your next embedded design. I've also included an on-screen link to another video for those of you more interested in the implementation itself, showing how to use the DMA with analog readings, serial communications, and waveform control in about 10 minutes without writing any lines of code using the Microchip Code Configurator, or MCC. Before moving on, feel free to like, comment, or subscribe if you're interested in learning more about these topics. Okay, so getting started. Have you ever noticed that a large amount of embedded system design revolves around simple but repetitive data movement, like storing a sensor reading in RAM or transmitting that sensor reading over a UART for a display or to a Wi-Fi module, or perhaps even varying a PWM based on a sensor reading to drive an output device like a motor or even just a simple LED? Well, all of these movements typically happen across a pipeline called the data bus, where, as you might have guessed, data is exchanged. Now, we can all recognize that if the CPU is handling data transfer, that program execution will be stalled until that data transfer is complete. So, these frequent data movements tie up the CPU directly as it must request access to the bus, pull in the data, increment source and destination pointers, and so on and so forth for each byte of data. Now, this can get even more complicated when dealing with interrupts because it usually leaves us with two choices. A, complete the data transfer before servicing the interrupt, which leads to interrupt latency, or B, put the data transfer on hold and then proceeding to what we were doing before. However, direct memory access lets you automate these simple but common data movements with zero CPU intervention. The DMA peripheral has two primary modes of operation. Firstly, it can stall CPU execution until a data transfer is complete, or it can utilize bubbles of unused instruction cycles that occur when the CPU is idle or waiting for an event. So at this point, you're probably wondering, but wait, if the DMA and the CPU seem to share instruction cycles, how does this really improve in performance? Well, rather than getting into the granular details of computer architecture and the memory pipeline, I'd rather start with a story about Harry. Now, Harry is a scholar, and as any scholar, he loves to spend time in his study amongst his books and papers doing research. But Harry's chores are constantly getting in the way of his work. Whether it be watering his plants when they are dry, going grocery shopping when he runs out of milk, or fetching his mail from the post office. Harry is sick of these constant interruptions to his scholarship, and so he decides to hire a butler. Now, every time he is interrupted with one of these tasks, he will simply tell his butler to go off and do the task for him. Harry's plan works well at first, but he begins to realize some major issues. Firstly, he notices his butler struggles with tasks that aren't repetitive and well defined. For example, his butler can fetch milk when the fridge is empty, but he can't sit there and determine the ideal fat content that's best for Harry's changing lifestyle habits. Secondly, he notices that the other issue is that the butler at times gets tied up with certain tasks. For example, the mail is delivered every other morning at an unspecified time, so the butler usually waits at the post office until the mail is ready to go. Now, this becomes a real issue when a more pressing task comes up, such as Harry running out of milk. It seems Harry didn't account for the fact that his tasks have a variety of conditions and circumstances that imply a level of priority or importance over each other. Now you might be thinking at this point that what Harry really needs is to get off his butt and stop being such a lazy bum. And while that might be true, isn't everyone? So why should he spend his valuable time doing things that almost anyone could do? To get around this issue, Harry decides to hire a couple more butlers and puts up a task manifest. The task manifest includes a priority level for a task, an event that triggers each task, and finally the task itself with an associated source and destination. Harry ends up spending a total of the same amount since he is only paying each butler for time spent on each task. The manifest allows the butler to figure out what needs to be done without interrupting Harry's work. Now let's take a step back and think about how this applies to microcontrollers. We can think of Harry as the CPU. His real strength lies in logic and computation. The butlers are DMA controllers and are useful for simple and repetitive tasks such as data movement. We can think of these items like the plant or the mailbox as other device hardware peripherals like an ADC or analog to digital result register or a UART receive register buffer. From a high level, this manifest usually consists of a source and destination module, each with its own message size that indicates how many bytes or messages the respective module can handle at one time, and some start, stop, and abort triggers that define when it operates. In more concrete terms, the first DMA mode allows us to quickly respond to events more quickly, similar to how Harry doesn't need to pack up his books just to check out his thirsty plant. The second mode allows us to utilize wasted instruction cycles that would have been lost anyways as a natural byproduct of the CPU maintaining its state. It even allows for some interesting low power applications, since the unused system clock cycles for a dozing CPU can still be used by the DMA controller. As you might have noticed, the whole point of this DMA and CPU collaboration is that we are given some amount of a shared resource in the form of a system clock that corresponds to the number of instructions available to execute code or move data. So really what this means is we can maximize the efficiency of our system by increasing throughput, while minimizing the overhead of switching between tasks. I'm going to end here since we are starting to go into broader concepts that are beyond the scope of this video. Hopefully this video helped shed some light on direct memory access on PIC microcontrollers. If you made it this far, check out the next video where we implement this without writing any lines of code and zero CPU utilization. I've also left links in the video description to some application notes and tech brief resources that show basic configurations and highlight some more interesting use cases utilizing DMA for things like arbitrary waveform generation and state machine automation. Please feel free to like, comment, or subscribe, as we here at Microchip love getting as much feedback as possible. Until next time, thanks for watching.